So let's look at this stuff. Let's say, sure, here's a good problem. Yeah. So the rate of growth of squirrels in the Arboretum. Oh, actually, sorry. This is not important at all, but I feel like I just have to show this all to you because it's worthwhile. It's going to be there. Well, we'll get there anyway. I'm going to show you something later. I'll show it to you right now. Nope, I'm not going to. It's because sorry, it's hiding in the place I give you to. Eventually, I have something funny to show you that I think will. So we're going to go with the squirrels in the Arboretum is proportional to the number of squirrels in the Arboretum. Oh, sorry, I knew that was going to happen. Cool. So what I wanted to show you all was this squirrel I saw this morning outside Dutton Hall, munching on a piece of pizza. It was kind of great. The squirrel looked like he was having a great day. Anyway, that's all. Just squirrel eating pizza. Good times. So rate of growth of squirrels in the Arboretum is proportional to the number of squirrels in the Arboretum. If there are 200 squirrels on the first day of spring, and there are 500 squirrels. I feel like I'm just making up numbers that are not very realistic, but that's okay. It's totally fine. No one cares really about the realisticness of questions. Let's say 500 squirrels. I don't know. I don't know how fast squirrels make babies. I have no idea. I'm just making stuff up. Let's say 500 squirrels 2 years later. How many squirrels will there be in another 2 years? Okay, not an unreasonable question. The key thing to focus in on here is this sentence right here. The rate of growth of whatever is proportional to the number of whatever. That's the thing that tells us how to write the differential equation, which tells us that we have exponential growth. So here we could, whoops, I'm all over the place. We could say that S of t is the number of squirrels at time t. And then if we wanted to, we could write the differential equation ds dt is equal to k times s. Come on in. Here for 16C?
Yep.
What's your name?
Josh.
Josh, I'm James. Nice to meet you. Come on in. We're just talking about how if you have the rate of growth of, in this case, squirrels being proportional to the number of squirrels, that's just a way of writing this differential equation. The ds dt, the rate of growth of squirrels, is proportional to or a multiple of the number of squirrels. And then when you solve this sort of differential equation, so you're going to see this kind of setup a lot. You don't want to really go through solving it every time. The solution here ends up being S of t equal to C naught e to the kt. We did this one on the last class last time, but we can do it again. So again, I'll say you don't want to do this every time because it's just the same work every time, but it is good to see it the first couple of times. So the reason this leads to this is because, well, if we're going to solve ds dt equal to k times s, I'm going to separate variables. ds dt equal to k times s. We're going to separate. We're going to bring all the s's to the left and all the t's to the right. So I'm going to divide both sides by s. I'm going to get 1 over s ds. I'm going to multiply both sides by dt and make k times dt. Now we're separated. All my s's are on one side, all my t's are on the other side. And I don't really care which side k is on, but I will say usually if you have a choice, we try to tend to put things on the side that the function is not on. since our function is s as a function of t, we're going to try and put everything else on the other side that's not on the s side if we can. It just makes it easier in the end. You totally could have divided by k as well, but it's just more work that way. So now we're going to integrate both sides. We integrate both sides, we're going to get the integral of 1 over s ds equal to the integral of k dt. The integral of 1 over s is the natural log of, I'm going to leave off the absolute value. So the integral is the natural log of the absolute value of s, but we don't really need the absolute value because it all works out in the end. So we're going to say it's the natural log of s, and it's equal to the antiderivative of k is just k times t plus some constant c. And now we're going to solve for s. We're going to exponentiate both sides. So e to the natural log of s equals e to the all that kt c. E to the natural log of s is just s. And we break this up into e to the kt times e to the c. And then e to a constant is just a constant. So we're going to call this c naught. So then we're going to rewrite this as s, or s of t, is equal to c naught times e to the kt. So when you start off with the rate of change of something is proportional to the amount of that something, it's always going to end with s or whatever we're talking about being an exponential function of t. And so we don't typically have to do all this work every time. Questions about that? So the words that the rate of growth is proportional to the population size, or is that the, oh gosh, there's another way of saying it as well. Or if you have exponential growth, or there's one other way, it's like if the, the relative growth rate is constant. Another way of saying, so these three phrases all mean the same thing. The relative growth rate is constant, or the rate of growth is proportional to population size, or the population grows exponentially. These all mean the same thing. Let me write them down. Let me write down exactly what they mean. So here's what the first one means, or actually, here's what the second one means. The second one is exactly what we just did. We started off with the rate of growth being proportional to the population size. Here's what the first one means. The relative growth rate is constant. What is a relative growth rate? Well, if I said the population is growing at 200 squirrels per year, that's not very useful information. You don't know how many squirrels there are, right? If there's 1,000 squirrels, that's a lot of squirrels. If there's 1,000,000 squirrels, 200 a year is not that many as far as your growth rate is concerned. So the relative growth rate is the growth rate divided by the population. So it's more meaningful. It tells you, oh, if my relative growth rate is like 0.2, that's a lot. It's kind of like 20%. Or if it's 0.0002, it's a much smaller relative growth rate because we're comparing it to how many squirrels there actually are. And if we're saying that's constant, look, these equations are the same equation. They're just written differently, but they mean the same thing. That's why I'm saying this, because so that when you see these sentences, you're like, oh, we're just talking about exponential growth. And so both of these equations really lead us to exponential growth, which is that s of t is some c naught e to the kt. Okay, so lots of things here. But the takeaway again is if you see any of these statements, you just know we have exponential growth of dk. And then the rest of it's just kind of just doing the math, meaning we're going to take our exponential growth model and we're going to plug in the information we have to find the answer to the questions being asked. So here's what I'm going to do. Okay, all right, we have s of t equal to c naught e to the kt. And we know a few things. We know in the beginning, the time equals 0. I have to look back and see there were 200 squirrels. And we know 2 years later, there are 500 squirrels. And then they're asking how many squirrels will there be in another 2 years later. So at time equals 4, we want to know how many squirrels are there going to be. Okay. Things so I'm going to use these two pieces of information to find C naught and K, because that's what we have to do before we can answer this question. So I want to find both that and that. C naught is almost always going to be the amount you have at time 0. Not almost always, it's always going to be. So the only reason you wouldn't know C naught right off the bat is if they didn't tell you how much you had to start with, which sometimes they will do in the problem. They'll be like, we have this many squirrels 2 years later, and this many squirrels 5 years later. How many did we start with? Or how many do we have 10 years after that? Then you have to work a little harder to find C naught. In this case, we don't. We can just plug this in and say, okay, S of 0 equals C naught e to the K times 0, but that's going to equal 200. E to the 0 is just 1, so you get C naught equal to 200. And then we're going to use that and say, okay, our new model, our updated model is S of t equals 200 e to the K times t. And then we're going to use the other data point where t is 2 and s is 500 to find what k is. So I'm going to say that S of 2 is equal to 200 e to the K times 2, but it's also equal to 500. And then we're going to solve for K. So divide both sides by 200, we get e to the 2K equals 5 halves. Take the natural log of both sides, you get 2K equal to the natural log of 5 halves. So K is equal to 1/2 natural log of 5 halves. Or however, if you want to write decimals, that's totally fine as well. I like fractions personally. So now here's our fully fledged model. Model for exponential growth is S of t equals 200 e to the 1/2 natural log of 5 halves times t. And now I want to find S of 4. I'm just going to plug in 4. 200 e to the 1/2 natural log of 5 halves times 4. And in this particular case, well, in fact, in general, when the amount of time is like a multiple of the time. So I would say my original time interval that was given to me in kind of the build up here was 2 years from time equals 0 to time equals 2. If your next time interval is kind of a nice even multiple of that, or I should say integer multiple of that, you can figure out the answer to this without actually having to use a calculator, because things work out nicely. If this was like a 7 here, it wouldn't work out so well. But since 4 divided by 2 is going to be an integer, this is going to work out real well. Here's what I mean. We're going to write this as 200 e to the 2 times natural log of 5 halves. Because 1/2 times 4 is 2. And then that 2 can come up as the exponent in the natural log. So I can rewrite this as 200 e to the natural log of 5 halves squared. But then e to the natural log of some stuff is just the stuff. So this is really equal to 200 times 5 halves squared, which is then 200 times 25 over 4. 200 divided by 4 is 50. 50 times 25 is, I don't know, it's 100 times 12.5, so 1250. That's how many squirrels there are going to be in another 2 years. Something that's interesting about exponential growth is that basically the multiplication factor of population is the same every however many years. So from time equals 0 to time equals 2, we multiply by how much? Like 2.5, right? 200 times 5 halves gave us 500. And from time equals 2 to time equals 4, you get the same multiplication factor. 500 times 5 halves is 1250. We went another 2 years, it would multiply by another 5 halves. You'll hear people say something like in exponential growth, the doubling time is constant. It's true for any multiplication factor, though. And any It's kind of not that important also, but sometimes you see these things, and I probably should say them. But it is true, when you're talking about exponential growth, the doubling time is always constant. So if we say like the population doubles in every 20 years, that means really exactly what I just said. In 20 years, there'll be twice as many people, and then another 20 years, twice as many people. That is another hallmark of exponential growth or decay. Questions so far? Okay, so we can talk more about that, but I think we should do some examples, yeah, where we talk about first or, oh, I know what I was gonna say. Some people asked, so I said yes. I'm gonna have office hours after class today. They're gonna be downstairs. I think someone's in here after us. I was gonna see here, but yeah, I'll be downstairs in I think 2211. I have an office hours. So if you want to come, feel free to come. You don't have to. No pressure. Let's talk about some other differential equations. So specifically, first order linear differential equations. When we say first order linear differential equations, we mean a couple things. So first order just means that the highest derivative that shows up in a differential equation is the first derivative. So the highest derivative is like y prime. You don't have any second derivatives or third derivatives or any other higher order derivatives, just first derivatives. And then the linear part means that you don't have any other powers of y. It's linear in the variable y. So only like a y to the first. No y squared, no square root of y, nothing that makes it non-linear in the y. So for example, I had a bunch of examples here. Okay. There they are. Cool. So here's kind of a very straightforward example. Y prime plus 2y equals x. It's definitely first order. It's only got the first derivative of y, no higher derivatives, and it's definitely linear. We only have a y to the first. There aren't any other weird things with y. Here's a non-example. Here's a couple non-examples. Y squared equals x times dy dx. Certainly first order, certainly solvable, but not linear. This is not linear or non-linear because of the y squared. You could totally solve this one though, right? We could definitely separate this. We could rewrite this as, I would probably rewrite it as dy dx equal to y squared divided by x. And then I would bring the y's to the left, 1 over y squared dy, and the x's to the right. And we could totally solve this. Or we're not going to, but you should. The other way we could be not first order linear is if we had higher derivatives. For example, if you had something like y double prime plus 5y prime plus 6y equal to 0, definitely linear. Is it linear? Yeah, it's linear. When I say so linear is kind of weird because you're like, what do you mean linear? Specifically, we're talking about the y, the function. Is it linear as far as y is concerned? Yeah, as far as y is concerned, there's only a y to the first. There's no y squared, there's no cube root of y, there's no cosine of y, and it's not multiplied by anything else. So yeah, it's linear in y, even though it feels kind of strange to say that. But it's not first order. This is not first order. It's the second order differential equation. Last quarter, the guy who took in this class was really kind of big on like first order, not first order, linear, not linear stuff.
So you couldn't just divide by one y prime, perhaps you can't do that?
No, we cannot just divide. No, we definitely cannot just divide. I mean, we could divide by y prime, but here's what it would look like. It would be y double prime over y prime plus 5 plus 6y over y prime equals 0. Right? We're allowed to divide by y prime. It's just sure you can divide by y as well, but again, it's not going to really do anything good for us. It's still going to look gross because when you have like y double prime divided by y prime, it doesn't simplify it any normal way. It's just a second derivative divided by a first derivative. On the other hand, this equation here is definitely a first order linear differential equation. And sometimes they can be solved by using separation of variables. This one can't. Definitely not separable. Sometimes they are though. So if we have a first order linear differential equation and it's not separable, there is a method in which we typically solve them. And the method requires what's called, well, first of all, the method is one, has to be written in the standard form, meaning it must be written exactly as y prime plus y times some function of your other variable, typically x or t, equals some function of your other variable. In this particular problem, our p of x is 2, and our q of x is x. So as long as you can write it that way, you can always solve the equation using what's called an integrating factor. Great, so let's do it. This one's not too bad. Some people are more kind of focused on people showing all their work when they solve this kind of thing. Other people are totally cool with you just jumping straight to the end. So I'll talk about how to show your work, and then we can talk about how you can jump straight to the end. So if I want to solve y prime plus 2y equal to x, I need to identify specifically my p of x. So I can see that p of x is indeed equal to positive 2. And not that we really need to, but q of x is equal to x. The professor did talk about this today a little bit. Did they use I or mu for the integrating factor? Mu, okay. Some people use an I because integrating starts with I, but people mostly use mu. So our integrating factor is mu of x, and it's equal to e to the integral of p of x dx, which in this case is going to be e to the integral of 2, which is just e to the 2x. That is our integrating factor. So what we're going to do is we're going to multiply the entire equation by the integrating factor. So I guess I should say step 1, write in the standard form. Y prime plus p of x times y equal q of x. Step 2, find the integrating factor. It's good to have steps. Mu equal to e to the integral of p of x. Step 3, that's where we're going to multiply both sides of our equation by the integrating factor. So we're going to multiply the entire equation by our integrating factor, mu. So in this case, we're going to get e to the 2x times y prime, e to the 2x times y prime plus 2y equal to x. That's going to give me e to the 2x times y prime plus e to the 2x times 2 times y equal to x times e to the 2x. Okay, here's the reason we do this. The entire reason we do this is because when you multiply both sides by this very specific thing, the left-hand side looks like it's the derivative of a product. Specifically, this did I say right-hand side? I meant to say left-hand side. I said right-hand. The left-hand side here looks like the derivative of e to the 2x times y. If I use the product rule, the derivative of y is y prime times the other thing, e to the 2x, plus leave y alone, and the derivative of e to the 2x is e to the 2x times 2 because of the chain rule. The easy way to always figure out what it is you just look at the term that has the y prime in it and you drop that prime. I'm looking here, I'm like, oh, e to the 2x times y prime, let's get rid of the prime, and e to the 2x times y is exactly the thing that I'm taking the derivative of using the product rule. Questions or comments or observations about this? It's kind of the crux of what's going on. Yeah, totally. So when I'm doing this process, if I'm trying to figure out what this left-hand side looks like, the derivative of, all I'm doing is I'm looking at the term that has the y prime in it, in this case, e to the 2x times y prime, and I'm dropping the prime. So I'm saying, oh, I'm just going to look at e to the 2x times y. And then the derivative of that is going to be exactly all that. Let's actually write it out. The derivative of e to the 2x times y, if I use the product rule, I've got two pieces, the first piece and the second piece here. The derivative of e to the 2x is e to the 2x times 2 because of the chain rule. And then I have to multiply it by the other thing, which is y. So if I want to use like f and g, this is f and this is g, here's my f prime, my g. Plus, now I switch it up, I do it the other way, I leave f alone. So I get e to the 2x. And then what's the derivative of y? Not quite. It would be if we were differentiating with respect to y, but we're differentiating with respect to x. So the derivative of y with respect to x is just dy dx, or y prime. The derivative, so I know it sounds kind of dumb, but the derivative of y is the derivative of y. It's almost like, oh yeah, we didn't have to do anything. But look, that's exactly what I have up here, written in the opposite order, but it's still the same thing. It's e to the 2x times y prime plus e to the 2x times 2 times y. So when we multiply both sides by the integrating factor, the left-hand side always turns into exactly the derivative of some product. And very specifically, or I should say very generally, the left-hand side is always just the derivative of your integrating factor times y. Kind of cool. And then the rest of this is not too terrible. So then we're going to say, well, rewrite the left-hand side. So that we have the derivative of e to the 2x times y equal to the right-hand side, which is x e to the 2x. But then if the derivative of something equals something else, we can integrate. Say, well, that means that just e to the 2x times y is equal to the antiderivative of x times e to the 2x. Right? If the derivative of e to the 2x times y equals that, then the derivative of e to the 2x times y equals the derivative of the antiderivative. I'm gonna take a minute to let that sink in for a sec. It'd be kind of like if I said the derivative of y is equal to x squared. How would I find y? Well, it's got to be the antiderivative of x squared. So if I take the derivative of this, I get x squared. So when the derivative of something is equal to something else, we can find that something else by anti-differentiating it. Okay, so we're almost done. Ooh, we're almost done, except now for the hard part, we actually have to integrate this right-hand side. And sometimes that's fairly straightforward. In this case, it's a little more work. We have to do integration by parts. This is definitely an integration by parts sort of integral. So we're going to get, let's see, u is equal to x, du is equal to dx, dv is e to the 2x dx, and v is e to the 2x divided by 2. So integrating it, we get the left-hand side is still e to the 2x times y. The integral of this is going to be u times v, so x times e to the 2x over 2 minus the integral of v du, which is e to the 2x over 2 dx. And then actually integrating that, we're going to get that e to the 2x times y is equal to x times e to the 2x over 2 minus e to the 2x over 2 times another 2 plus c. Finally, the last step, divide both sides by the integrating factor. Or in other words, solve for y. Now, importantly, and this is important, everything on the right-hand side has to get divided by, in this case, e to the 2x, even the constant c. So here we're going to say that y is equal to 1 over e to the 2x times all of this. X e to the 2x over 2 minus e to the 2x over 4 plus c, which if you want to distribute it, is going to look like x over 2 minus 1/4 plus c over e to the 2x. Kind of funky, but is a solution, is the solution. So this is the very long way of doing it. It's a fair number of steps. Let me briefly mention kind of the thing people are often okay with their students doing for this kind of process. That's the long way. Let me just write down what the shortened version. Here's the short version. We'll use the same example. So we still have y prime plus 2y equal to x. So here's what we're going to do, which is, y prime plus p of x times y equal to q of x. So we're still going to find the integrating factor. So I should say 1, make sure it's the right form. 2, integrating factor is going to be e to the integral of p of x dx, which in this case is e to the 2x. And then you can jump straight to kind of the answer. The solution is that y is going to equal 1 divided by your integrating factor times the integral of q of x times your integrating factor. Now, let's write that down. So we're going to get our solution is going to be y is equal to 1 over e to the 2x times the integral of q of x, which was x, times mu of x, which is e to the 2x. Now, we're not done at this stage. We still actually have to do this integral and then multiply it up. But this is the solution and it's not very solved that far. And if you look back at the work we did, this is exactly what we got. Right here, here's the integral of q of x times mu of x. And then we ended up dividing by the 2x, which is exactly the same thing we've written here. Right, we just haven't done it yet. So this is kind of the short version. You find your integrating factor, and then you say your solution is 1 divided by that times the integral of q of x. Now be careful here. Don't do the dumb thing I used to do when I first learned this. I was like, oh, well, it looks like I totally just cancel out those mu of x's. It does not work. Right? You have to multiply these together and then integrate before you divide by mu of x. So the mu of x's definitely do not cancel in any way, shape, or form, unfortunately.
So the C's don't put them because he did it in there and he said they canceled out.
Wait, say that one more time.
For the C's plus C.
So the C definitely does matter for this first order linear differential equation. So if you look back at our solution, right? So I definitely, when I integrated this, we definitely did get a plus C right
For
here.
the mu of x,
Oh yes, the mu of sorry, yes. The mu of x, we definitely do not need the plus C. Also, if there's any absolute values, we completely ignore them without even thinking about it. If you're fine for the integrating factor mu of x, yeah. Good point. Other questions about this? Let's look at, we got time for at least one more example. Yeah, let's look at another example. So, yeah, and let's look at an example where we have to do a little bit of work first. So let's say our initial example was something like, sure, that's going to be fun. 2x y prime plus y equal to x squared. That's kind of boring. That's fine. Okay. So when I'm looking at solving a differential equation and I'm taking 16C, I always know it's going to be one of two things. It's either going to be separable, like we talked about in class really on Monday and a little bit on Wednesday, or it's going to be first order linear, which is what we just did. So I usually try to ask myself first, is it separable? This one's not, right? If I try to separate them, well, I would try to isolate the y prime. So I'd have 2x y prime equal to x squared minus y. And once you've got subtraction or addition over on this other side, it's usually a pretty good bet the separation is not going to work out. But if I try isolating y prime is x squared minus y divided by 2x, or dy dx equals, see, now I have a problem because there isn't really a nice way of getting y over to the other side without bringing some of the x along with it. So it's definitely not separable. So if it's not separable and someone said to solve it, that means we're only left with one other option. It's got to be first order linear. We don't have any other methods of recourse in this class, which is good. Nice not to have options in this class. It means it's either one thing or the other, and if it's not that, then it's the other thing. But to use first order linear, we first have to write it in the standard form. Meaning it has to look like just y prime plus some function of x times y equal to some other function of x. Meaning we need to divide everything by 2x. So I'm going to get y prime plus 1 over 2x times y equal to x squared over 2x, which I should simplify. So that's the all important first step is we need to get y prime by itself like this, see what's multiplying y. So here's our p of x. And here I would simplify this to x over 2, but there's our q of x. And I always really don't feel good about doing it, but I guess we could just jump straight to the solution, even though it feels like I'm depriving you of an opportunity to see something. Well, let's do it one way, the fast way. So jumping, well, actually, before I do that, I have to find the integrating factor, right? So integrating factor. The integrating factor is going to be e to the integral of 1 over 2x dx. And I would probably, before I integrated that, bring out the 1/2. So I would write this as e to the 1/2 integral of 1 over x dx. And what's the integral of 1 over x? Yeah, so normally I would write the natural log of the absolute value of x, but we don't care about the absolute value of this integrating factor. So we're just going to write natural log of x. And no plus c. Now, it is usually in your interest to simplify the integrating factor as much as you can. Especially if you see a natural log in the exponent, that means you're going to want to take whatever coefficient you have here, put it up in top like that, and then say that you have e to the natural log of x to the 1/2, which is just x to the 1/2, or if you prefer the square root of x. It's definitely better than writing e to the 1/2 natural log of x. It's also going to make it so it's easier to do our integration, right? I don't want to try and integrate this times e to the 1/2 natural log of x. I want to do this times x to the 1/2. That's way easier. So definitely, it's in your interest to simplify this. But I guess we can just jump straight to, well, we're not jumping straight to the solution, we're skipping all of the middle work. So our solution, which we still have to actually do, is going to be y equal to 1 over the integrating factor times the integral of q of x times your integrating factor, which is going to be equal to, so our integrating factor is x to the 1/2, so it's 1 over x to the 1/2 times the integral of q of x, which is x over 2, times mu of x, which is x to the 1/2. Okay, so now we actually have to multiply these things together and then integrate that. So we're gonna get 1 over x to the 1/2. I might rewrite that as x to the negative 1/2. So x to the negative 1/2. I might also pull out the 1/2 constant in my integral. And then x to the first times x to the 1/2 is x to the 3/2. So then when I integrate that, I'm going to end up getting, I'm going to put the 1/2 first, 1/2 times x to the negative 1/2 times the integral of x to the 3/2 is going to be x to the 5/2 times 2/5 plus a constant. I don't like to leave it like this. I don't know why. Plenty of people leave it like this. Totally fine. I like to distribute it for some reason. So if I distribute this to each term, 1/2 times 2/5 is going to be 1/5. X to the negative 1/2 times x to the 5/2 is just x squared. And then 1/2 x to the negative 1/2 times c is going to be c times x to the negative 1/2. You could say divided by 2, but since we don't actually know what c is, you could just say c divided by 2 is a new constant, call it c. So again, I'll say, I don't personally love skipping all of the middle stuff where you multiply both sides by the integrating factor and then show the left-hand side as the product rule and then integrate both sides. But depending on what your teacher wants, that might be totally fine.
So can you explain why it is separable?
Sure. So to be separable, you have to be able to write essentially to be separable, you have to be able to write dy dx is equal to a function of x multiplied by a function of y. And to me, so really what that means is once you've isolated dy dx, the only things you're allowed to do after that really are multiplication and division. And there's no way using multiplication or division to really get y over to the left-hand side. I have to use addition, and that's just not going to work out because you don't want y plus dy, you want y times dy because we can't integrate y plus dy. But yeah, it's not separable. So usually addition and or subtraction are the barriers to a differential equation being separable. Question. Like the actual, like the long way, or just this last part here?
Just that spot at the bottom.
Sure. So here's my solution. And then I just wrote that. I wrote 1 over mu times the integral of q. Right, there's my q. X over 2, right? Because I simplified the x squared over 2x to x over 2. And here's my mu again. So what I did was I brought out the 1/2 here. And I said x to the first times x to the 1/2 was x to the 3/2.
I combined it.
Yeah, well, and it just wasn't like, it wasn't because I just wanted to, it's because I kind of have to. I can't really integrate x to the first times x to the 1/2 without first multiplying them together and then integrating the results.
You always have to combine q and q.
Combine. I wouldn't say necessarily, like if q was x, like in the previous problem, when one of them was x and one of them was e to the x, there isn't really a way of combining it. You have to use integration by parts there. But if there are functions that can be combined together, it usually makes sense to do so. And after that, we integrated the x to the 3/2 and got 2/5 x to the 5/2 plus c. And then we distributed the 1/2 x to the negative 1/2 to each term. 1/2 times 2/5 gave me 1/5. X to the negative 1/2 times x to the 5/2 gave me x squared, or x to the 4/2. And then when I multiply this by this, I got 1/2 c times x to the negative 1/2, but I said 1/2 c was just a new constant, and I called it c again, which is very, very typical. Time is it? Not enough time to do the problem. Let's see here. There was something else I was going to say. Oh, I know what it was. Sometimes some of these equations are both. What I'm looking for. Both, holy smokes, separable and first order linear. Let me show you what I mean. So for example, if I have something like y prime minus x squared times y equal to x squared, this is definitely, in addition to being first order linear, in fact, let's talk about how it's first order linear. So to be first order linear here, or I should say, to be solved with an integrating factor. Now here's where you have to be extra careful. my P of X is what in this problem? Usually we're writing it as Y prime plus P of X times Y equals Q of X. So my P of X here is negative X squared. You have to capture the negative. You might consider rewriting this as Y prime plus negative X squared times Y equal to X squared, just to be extra careful there. Excuse me. So then our integrating factor here would be e to the integral of negative X squared, which would be e to the negative X cubed over 3. And you can totally do the work, be fine. But I will just point out, this is also separable. If we isolate Y prime, so Y prime equals X squared plus X squared times Y, it is very possible to write the right-hand side as a function of X multiplied by a function of Y, because I can factor out the X squareds that happen to be the same. So I could totally rewrite this as dy dx equal to X squared times 1 plus Y. And then I can bring the Y's to the left and the X's to the right. And then I can integrate both sides. So both methods will work here, and both methods will produce essentially the same result. They might look slightly different by a constant, but they are essentially the same. We haven't finished it, but they would. Go ahead.
What if you don't separate it?
Then you can do it the other way. You can do it this first way. All right, so we could totally have not done this at all and said, well, I'm just going to use integrating factor. So my solution is going to be, let's see, it's going to be y equal to 1 over my integrating factor, e to the negative x cubed over 3 times the integral of my mu of x times q of x. So it's going to be x squared times e to the negative x cubed over 3. And this is totally doable. You can integrate this last part just by doing a nice u substitution, letting u equal negative x cubed over 3 and du equaling negative x squared dx, or negative du equaling positive x squared dx. So it totally works either way. It just depends on how you want to see it. Most of the time, you only have one option, but sometimes there are problems that can be done either way. And I guess I could finish it, but I should also probably stop talking since it's 2 o'clock. So good stuff. So integrating factors are a little what's the word for? I don't know. They can feel a little challenging. Feels like there's kind of a lot to deal with there. You all should definitely let me know on Monday if you know whether your teacher wants you to kind of show all the work or if he just wants you to jump straight to the end. Okay. Usually there's one person who's like, no, show all the work, and it's usually the Dell. Everyone else is like, just jump straight to the end. So it's still good to know why we're able to jump straight to the end, but you don't have to show all that.